Welcome everybody to another exciting episode of Fluid Earth Dynamics. Today we're going to talk about sediment mass balance, which is expressed via something called the Exner equation, named after a German meteorologist named Felix Exner, who first proposed it. And sediment mass balance doesn't necessarily sound like something that would make you want to wake up in the morning, but actually it's pretty fabulous because this is the equation that basically governs the evolution of topography on the Earth, and it's surprisingly simple. We're just going to spend a few minutes doing some bookkeeping. We'll get out of that a basic governing equation, and then in class we'll come up with a variety of different exercises and things to try it out. So that's what we're up to in this video. So moving on. The basic goal here is to try to relate the dynamics of topography, and so by that I mean things like this. I've got an image of a dune here that you can see outlined. That's made of sediment, and it's moving, so it's dynamic topography. It's changing and evolving with time. And we want to understand how to relate those changes in topography to the variations in sediment flow over the bed as indicated here. So this area is a place where you can see the sediment flow particularly clearly. It's suspended sediment in the lee of this dune. And I want to emphasize that though I chose a dune as an example, this applies to all kinds of topography, from mountains to swamps and from the top of Everest down to the deepest part of the ocean. So the elements of the balance that we're going to consider are basically in three layers, you might say. So starting down here in this diagram, we have bedrock. So we're going to start at bedrock. We're going to distinguish between bedrock and sediment. So the sediment would be the loose material above the bedrock. And then above that, we have some kind of a flow. Now, I'll probably at some point refer to it as water because that's most of the flow that I work with, but it could be a flow of anything, air, even ice, what have you, debris. But for the most part, you can think of flowing air and water here. And we've got a few terms here that we want to highlight. We'll define our bed elevation, or the elevation of our sediment surface is eta. So that's this white line here, and that is the elevation of the sediment surface. And actually, I should be clear here, it's the elevation of the Earth's surface. Below that, we have an elevation of the bedrock surface, eta b. And then at the top, we have h, the depth of the flow. And the main quantity that we're going to be trying to track here is the flow of sediment over this surface. So that's denoted by this flux Qs. And to go any further, we're going to move on to the next slide. So actually the other thing I should do, though, in this one is to define the Qs. So now we've used little q in this course in a couple of different ways, and this one is analogous to the way that we did for water discharge. This is the discharge of sediment in volume of sediment per unit width of flow and per unit of time. So that's volume sediment flux per unit width. So sediment flux implies the time. So the units of this are volume divided by time divided by width. So it's length squared over time. Oh, there's one other important piece of this slide that I should mention. We're not going to use this right away. We'll come back to it at the end. And that is that this arrow here denotes the fact that we are interested as geologists in the possibility that bedrock may rise or fall. So this would be tectonic effects, uplift and subsidence, and the rate of rise or fall will be denoted by VB. So it's positive if it's uplift, it's negative if it's subsidence, and we're going to skip this for most of the rest of this talk, but we'll come back to it at the very end and see how this is incorporated into our mass balance. Okay, so we're going to zoom in now, and for the moment we're going to forget about the bedrock part of this and just try to do a mass balance for the sediment surface, assuming that the bedrock is far below us and is not moving up or down. So doing that, we're going to set up the usual control volume type approach where we take a slice of our surface and we're just going to do a very careful mass balance, a flow balance of mass in and mass out of that slice. And actually, because the sediment we're going to assume has a relatively constant density, we're not even going to worry about mass. We're just going to do this in terms of volume. So if you think about the balance of mass in this little slice that I've outlined in black dash here, the flow rate in is shown over here. So we have a flow of sediment into the little box, and that's denoted by QS, and it's taken at location X, so X is right here. And go away. And that's the flow rate of sediment into this box. And remember, it's in volume per unit of time per unit of width. On the outgoing side, the downstream side of the box, we have another flow, and that's given by QS, but now taken at location X plus dx. So we've stepped a little bit downstream. We've stepped a distance dx downstream, and we're taking our volume per unit width per unit time value, QS, at this new location, x plus dx. And if you look at the geometry of the figure, and remember that we, as always, we define x as positive in the downstream direction, the out part of our volume balance is taken at the downstream edge of the box, and the in part is taken at the upstream edge, because that's how we've set up our flow system. Okay, so that's everything we need to know here. The only other piece of this is that we are going to have to pay attention to sediment that is stored in the flow column, and let me just say the water column for now, although this could just as well be air. And that sediment is denoted by a concentration of sediment as a function of vertical elevation y, and that concentration is just volume of sediment per volume of fluid. So that's C of y, and I've kind of indicated it with this little gradient of yellow here. So these are the elements in our mass balance, and in the next slide we'll just write those down explicitly in math. So the inflow was QS, taken at x, and now I want to do everything in terms of volume. So to get to volume from QS, I need to multiply by the width, because this is volume per unit width, and I need to multiply by some time interval, delta t, because it's volume, this one, QS, is volume per unit width per unit time. So if I multiply by width and I multiply by time, I end up with what I want, which is sediment volume in. So this piece here represents the volume of sediment flowing into our little slice. Stepping distance dx downstream to get to the outgoing part of our little box, we have a volume flow out per unit width per unit time. That's QS evaluated at x plus delta x. And I think I switched up from dx to delta x, but they mean the same thing. And then again multiplied by width to get over that normalization, and then multiplied by delta t to get us back to total volume. So volume per unit width per unit time times width times time interval, and we have once again a volume out. So we have volume in and volume out. Very simple. There are only two places that any imbalance between those two volumes can be accounted for. And let's suppose, for the sake of argument, that more is coming in than is going out. So let's say for the moment that we have a positive balance. That sediment can either be added to suspension, so we can increase the amount of sediment that's stored in the fluid, in effect, and we find that volume by taking the concentration at each elevation in the flow. We sum those concentrations over the entire depth of the flow, because as far as storage is concerned, it doesn't matter whether the sediment is stored at the bottom of the flow or the top. So you know that adding up in calculus means taking an integral. So we take our concentration, integrate over y, and we do this over the entire height of the flow, which is from eta, the bed, to eta plus h, the top of the flow. And then to get from that number, which is in terms of length, to total volume, we multiply by the width of our, or the downstream extent of our little slice, that's delta x, and its width, which is b. So this quantity has, again, the dimensions of volume, and you should check that for yourselves. Remembering that c is non-dimensional. It's the fraction of sediment in the flow by volume. And then the other place that any sediment imbalance can be taken up, and if we say that there's an excess coming in than going out, then that would be taken up as positive storage, would be in the bed. And that's actually the part that we're interested in. So the way that sediment would be absorbed into the bed is for the bed to increase in elevation. So that increase in elevation would be delta eta, because remember that eta is the elevation from some fixed unchanging reference to the top of the sediment bed, multiplied by our streamwise extent of the box, delta x, and multiplied by the width of the box, b. So we've just got vertical, so we've got the height of the change, we've got the length of the change and the width of the change. So we've just multiplied the three dimensions of our our little notional sediment volume that was added or subtracted. And the only other thing we have to do is pay attention to the fact that the bed is not made 100% of sediment. It actually has pore space in it, and so in effect, if I put some volume of mineral sediment into the bed, I get more than that volume of bed deposit because I get some pore space added for free. And that is accounted for by including this volume concentration C0. So the volume of actual mineral sediment added to the bed is a little bit less than would be indicated by the rise in the bed because some of it is taken up as pore space, C0. So these are our four elements: in, out, in taken at the upstream end of the box, out taken at the downstream end of the box, and then two potential storage terms, one storage into suspension and the other one storage into the bed. So we're just going to put those together in a single equation and add them up. So the total gain or loss is the sum of the two storage terms, storage into suspension and storage into the bed, and that has to be balanced by influx minus outflux. So if you think of these as the gain or loss from your checking account, in fact, let's say that you could think of this one as being like the gain into your savings account, this one as being like the gain into your checking account. So two places that any excess money can go into in your financial world, and that has to balance any difference between the amount of money that you take in and the amount of money that you spend every month. So you could think of this as being kind of like a very simple financial balance, checking account balance, except that it's sediment mass. So two storage terms, one in the flow, one in the sediment bed, an influx of sediment and an outflux of sediment. And we've just put those together in one equation and summed them up. So now we're just going to do a little bit of algebra. We're going to divide through by the width of the box B multiplied by delta X multiplied by delta T, and this is just to get us from an awkward-looking equation into something that we can write and understand in terms of calculus. We're going to rearrange the terms and, as usual, pass to the infinitesimal limit when delta x and delta t are replaced by dx and dt. And we're going to remember the definition of the derivative, which is that, in this case, the derivative we're interested in is the spatial gradient in x of the sediment flux qs. And we're going to remember that the derivative is always defined as the dependent variable evaluated at the more advanced position minus its value at the less advanced position. So in this case, we take x plus dx, evaluate qs there, subtract off the qs value at x, and then we divide through by the interval distance dx. And that's how the derivative is defined. So if we do that and put our terms together, we end up with this fairly simple-looking equation. The two input and output terms ended up added together, well, they actually were subtracted, sorry, and then normalized by dx to get the derivative. So they're both folded into this, and if you go back to the last slide and remind yourself of the definition of the derivative, you'll see how that works. This is our storage into the bed term that we talked about, and this is our storage into the flow term. This one, again, represents the imbalance between input and output. And remember that the reason that it is there in the form that it is because the sediment in is taken at the upstream end of the box, the sediment out is taken at the downstream end, and the difference in the limit as dx goes to 0 is just this derivative. So the three terms add up to one fairly simple equation, and this is the basic Exner equation. It says that any imbalance between input and output is taken up either as storage into the flow or storage in the bed. And you can see, in a very crude sense, these three terms illustrated in the slide that we started with. So the bed elevation, changes in the bed elevation refer to changes in the elevation of our, in this case, our sand dune. This dq/sdx gradient term would refer to imbalances or changes in space in the sediment flux as we move along the dune. And then this term here would refer to any changes in the sediment stored in the transported sediment above the bed. So those are our three terms in the Exner equation. And let me just end this part on the Exner equation with a note on an alternative that you commonly find and a somewhat counterintuitive, I think, aspect of this equation. And that is human beings, for whatever reason, have a tendency to think of erosion and deposition in terms of speed of flow. So it's easy to think that a fast-moving flow is going to erode and a slow-moving flow is going to deposit. But if you go back and look at the equation, you can see that there's nothing like that in this. So erosion and deposition are represented by this term, and they really are just about the sign of this term. Deposition is when dA to dt is positive and the surface of the bed is rising, and erosion is when dA to dt is negative and the bed elevation is falling. And you can see that if we ignore for the moment any changes in storage of sediment in the moving sediment, the sediment flow, if you like, the transport system, in order for the bed to, say, deposit, this dqs dx has to be negative. So in other words, if this is positive, you're putting more sediment into some location on the bed than you're taking out, and dqs dx is negative. That is, the flow rate of sediment, qs, as we go downstream is falling, is negative, and vice versa if the system is eroding. But neither of those has any direct connection to how fast the flow is moving in general. So a fast-moving flow can be depositional if it's losing sediment as it goes downstream, and a slow-moving flow can be erosional if it's picking up sediment as it moves downstream. And I put in for contrast this diagram over here, which is called the Hjulstrom diagram, which is quite misleading, which indicates for any given grain size of sediment that a faster-moving flow would be more erosive and a slower-moving flow would be depositional. That's simply not the case. So don't use the Hjulstrom diagram. It's very misleading, even though you still see it reproduced in textbooks. So the last thing I want to do in this segment of class is to return to the diagram that we started with, and remember that as geologists we're also interested in cases where the bedrock can rise and fall. This would be vertical motion of bedrock due to tectonic effects, and we would typically refer to these as uplift or subsidence. And luckily, we don't have to modify our Exner equation very much at all to include this effect. In fact, adding back in possible changes in bedrock elevation involves nothing more than putting in an additional term that is paired with our rate of rise or fall of the sediment bed. The additional term refers to the rate of rise or fall of the bedrock itself. So this is, we denoted this as VB, the velocity in the y direction of the bedrock surface, and if it's positive, the bedrock is going up and we have uplift going on, and if it's negative, we have subsidence going on, and typically that would be associated with net deposition. So in class, when we do some exercises with this, we're going to try different versions of this. We're going to look at the Exner equation from a variety of points of view and see how it behaves in a variety of limits so that we can understand how it actually does reflect the dynamics of topography and changes in the surface elevation of our planet. So we'll do that, though, in class. Bye-bye.